Hello class, welcome to the second module of CHM 322, Physical and Structural Chemistry 2. We began this course by looking at what stereochemistry is all about. We considered enantiomers, we looked at diastereomers, we looked at different types of constitutional isomers that we have as a review of what you already know about isomers. And then last class, we were able to conclude on how to identify chiral centers or chirality centers in a molecule. Today, we are going to proceed by looking at optical activity. Now, what do we mean by optical activity? First, you need to know that light restricted to pass through a plane is plane polarized. Light restricted to pass through a plane is plane polarized. I will explain what that means as we go ahead. Plane polarized light that passes through solutions of a chiral compound remain in that plane. We shall see images that demonstrate this very clearly. When a plane polarized light passes through solutions of a chiral compounds, don't forget chiral compounds are those ones having a chiral carbon, that is a carbon that is attached to 4 different substituents. While achiral compounds are the ones that do not have 4 different substituents around them. That means they do not have chiral centers. Whenever a plane polarized light passes through such solution, the light will remain in that plane. That means the light will not change direction. The light will remain in the plane. Also, solution of chiral compounds rotates plane polarized light, and the molecules are said to be optically active. Now, on the contrary to achiral compounds, when we have a solution of chiral compounds, it rotates a plane polarized light, and the molecules are said to be optically active. So whenever you see, we observe that a molecule rotates a plane polarized light, then we say that molecule is optically active. Now, light passes through a plane polarized light. The plane polarized light is rotated in solutions of optically active compounds, like I said, that is chiral compounds. It is measured using an instrument we call a polarimeter. And the rotation is measured in degrees. The rotation in degrees is called specific rotation, which is symbolized using this alpha in a square bracket. Now, when we have a clockwise rotation, we call it dextrorotatory, sorry. When we have an anti-clockwise rotation, we call it level rotatory. So we have the dextrorotatory and the level rotatory. Dextrorotatory is when we have clockwise, level rotatory is when we have anti-clockwise. Now, if the light appears to have turned to the right, that is clockwise, we call it dextrorotatory, like I said, and we symbolize it. We show the symbol, sorry, using a D to show that it is dextrorotatory, or we use a positive sign. So whether we say positive or I say dextrorotatory, I'm still talking about the same kind of optical response. If it turns to the right, which is clockwise. Clockwise is the direction of your clock. Your clock moves from left to right around the clock circle. So that means the direction of the clock is what we call dextrorotatory. What if it turns to the left? We call that one anti-clockwise, which is your level rotatory, and we represent it with the L or with the negative sign. So it is the L or the negative form of that compound. Now, but sometimes we have cases where we have a racemate. When do we have a racemate? A racemate is when we have 50-50 mixture of the 2 enantiomers, that is the dextro and the level. The dextro and the level, or the plus and the minus. We call that a racemic mixture. Such a compound is called a racemate. Such a compound is called a racemate. Don't get this confused. The compound can either rotate a plane polarized light to the right, or rotate a plane polarized light to the left, or such a compound will not rotate a plane polarized light at all, yet it has a chiral center. Don't forget that every achiral compound will not rotate a plane polarized light at all, but there are some compounds that are actually chiral, and yet the plane polarized light will not be rotated. Why? Because they have what we call a 50-50 mixture. And the implication of this is that the opposite optical effects of each isomer cancels each other out. That means when we have the dextro-rotatory part, that is the positive form, rotates the light 50% to the right, while the negative form, which is the level rotatory, rotates the light to the left. Both of them will cancel each other out, and at the end of the day, the plane polarized light will remain in the same position. So we call such a compound a racemate or a racemic mixture. Now let's look at measurements of the optical rotation. A polarimeter measures the rotation of plane polarized that has passed through a solution. Don't forget, I said we measure the rotation of a plane polarized light using a polarimeter. The source passes through a polarizer and then is detected at a second polarizer. We shall see that in an image very soon. The angle between the entrance and the exit plane is the optical rotation. Now look at this diagram. This is our light. This is our light source. You can see this is an unpolarized light. A polarized light is a light that is traveling in a specific direction. It is not, you see, your normal light, the light you get from your bulb, that is the light you have in your house on your bulb, those kind of lights are unpolarized because they move in several directions. They don't have a specific direction. But when we pass it through a polarizer, the lights begin to move in a single direction. You can see I've passed this light through a polarizer here, and then it becomes a single direction light. You can see the light. Now, this is our sample tube, which contains the organic molecule. Now, when the light passes into the sample tube, if the molecule in the sample tube is chiral, what will happen is that the polarized light, which is moving in a specific direction, will begin to rotate. Look at the way it begins to rotate inside the tube containing the compound. It begins to rotate, and then we have another polarizer, which we call an analyzer. This analyzer is also a polarizer. It will help us to analyze the light. So by the time the light gets to the analyzer, the angle of the light from the eyes of the observer is what we will measure, and that's what will tell us what is the optical rotation. Now, what is the concept behind this? You say, what angle are we going to receive here? How do we know the angle of light that will be received here? It's simple. When you set your first polarizer, before you start the experiment, we adjust the analyzer such that no light is coming from the polarizer to the analyzer. We adjust them such that they are in such an angle to each other that no light can pass through the polarizer to the analyzer. That's one we do that using a blank. That means we do not put any molecule in the tube, so that we can use that to test that our polarizer is working fine and there is no light coming out on the other end of the analyzer. So what we now do is then we now put our compound inside the sample tube, and then we let the same light go through. Normally, we know we are not supposed to see any light if that compound is not chiral. If the polarized light comes the same angle at which it was earlier when we use the blank, we are not supposed to be seeing any light. But once we can see a light, it means that this compound that is inside the tube is optically active. That means it has rotated the plane polarized light. So the angle of that rotation, that means the amount of light we can see, the angle it is forming, you can see here now, you can see the amount of light the observer is seeing. The angle it is forming is being calculated here as the specific rotation, that is alpha, specific rotation. Okay, let's see here. Look at, for instance, this is our plane polarized light. We have already passed this light through a polarizer. Then it goes into our tube, which is our sample tube. This sample tube is containing what? Tartaric acid. Tartaric acid is optically active because it has chiral carbons. So once it passes through tartaric acid, what happens is that when it comes outside, the plane polarized light will be rotated. Now look at the plane polarized light is rotated clockwise. Can you see the direction it is moving? It's moving from here. It moves this way, like this. So it means it's moving clockwise to the right. Movement to the right, you can see that. And it's moved to this point. So now what we have here is a tartaric acid in the dextrorotatory form. That is, this will be our plus tartaric acid, plus form of tartaric acid. What if we have the same light passing through, the same polarized light passing through the same tartaric solution, and then when it comes outside, we are still having, okay, in this case, I said this is a racemic acid, not tartaric in this case. It can be any acid. If it is tartaric, it means that we are going to be having 50% of dextrorotatory tartaric acid and then 50% of the level rotatory tartaric acid, meaning there will be what? Racemic. There will be racemic. Don't forget I told you racemic mixture, meaning that they have equal number of both forms, that is both the positive and the negative. So what will happen is that the plane polarized light will remain unchanged. Why? Is because RA is not optically active. RA is not optically active because the positive and the negative will cancel each other out. The positive and the negative. So when it rotates, let's say this is 45 degrees, for instance, if it rotates 45 degrees to the right, that is the dextrorotatory form, because there's also 50% of the level rotatory, it will also rotate 45 degrees to the left. 45 plus 45 minus 45 equals 0. So at the end of the day, the rotation will still remain the same. There will be no rotation. So we say the RA, which is a racemic acid, is not optically active. So specific rotation, to have a basis for comparison, divine specific rotation, which is our alpha in a square bracket with our D to represent our specific rotation for an optically active compound. This is our observed rotation. This is equals to, that is our specific rotation is equals to our observed rotation divided by the path length times the concentration. You see it in a better form. Okay, mathematically, we have your specific rotation, which is your alpha in a square bracket, is equals to observed rotation, which is your alpha, divided by length, which is your path length. The path length is the length of the sample tube that we are using. The length of the sample tube will determine the specific rotation. So it's also one of the determinants, times the concentration of the compound. The concentration of that compound in the sample tube will also determine what the specific rotation will be. So this will be equals to degrees, of course, which is our alpha is measured in degrees. Our length is measured in dm, decimeter. Please do not make a mistake to measure your length in meters. The unit for your length is supposed to be decimeters, and then your concentration is in gram per mil, not in mole per dm cube. Concentration is measured in gram per mil, length is measured in dm, and your alpha, of course, is always in degrees. So specific rotation is that observed for 1 gram per mil in solution in cell with a 10 centimeter path using light from sodium metal vapor, which has 589 nanometers. This is just the standard way in which it is measured in the laboratory. We use 1 gram. The specific rotation is just 1 gram per mil in solution in the cell with a 10 centimeter path length using light from sodium metal vapor. So that's what we use in the laboratory. Now let's see a worked example. A 1.50 gram sample of quinine was dissolved in 10 ml of ethanol and placed in a sample cell of 5 centimeter path length. The observed rotation at the sodium D line was 1.21 degrees. This is the observed rotation. This is the gram, and this is the solution. This is the mil. This is our path length. So how do we solve this question? We have to calculate for the what? Let's calculate for the specific rotation. In the question, don't forget we're given the observed rotation already. We have to look for the specific rotation. Let's see how to solve this. What were we given? Well, first we're given the length. The path length of the sample tube is 5.00 centimeter. We have to convert that to decimeter. Don't forget I told you that we must use our values in decimeter. So how do I convert from centimeter to decimeter? All I need to do is divide by 10. When I divide centimeter by 10, I'm going to get decimeter. Do not forget this. So 5.00 divided by 10 will give me 0.500 dm. Now, my alpha, which is observed rotation, was given to me 1.21 in degrees, of course. So we already have this in the correct unit. And finally, concentration was not given directly, but I was given the gram, that is the mass, and I was given the volume of the solution in mils. And don't forget, we need our concentration in gram per mil. So all I need to do is say gram, which is 1.50, divided by 10 mil, which will give me 0.150 gram per mil. Okay, so if I apply the formula, this is the formula, don't forget, specific rotation is equals to observed rotation divided by length times concentration, path length times concentration. So from here now, I have my observed rotation will be equal to, what is the value of my observed rotation is plus 1.21. Don't forget, this is plus. If it were to be negative, I'll be given in the question. So it is plus, and then I'll divide that by my length, which is 0.500 dm, times my concentration, 0.150 gram per mil. These units are very important for you to arrive at the correct answer. My specific rotation for this question is plus 16.1 degrees. I encourage you to lay your hands on several other questions to test yourself on solving this question, because so many times the problem you most face solving this problem is issue of converting the units. You must use this correct unit. If not, you will not arrive at the answer. Your length must be in dm and your concentration must be in gram per mil. Specific rotation and molecules. Characteristic property of a compound that is optically active, the compound must be chiral. So note that before a compound can be optically active, it means that compound is chiral. And you already know by now what it means for a compound to be chiral. It has to have what? A tetrahedral carbon, which has 4 different substituents around it, which we call a chiral center. Is that okay? So, and we've seen how to identify chiral centers in molecules in our previous module. So if you do not know that, go back and watch that video and understand it properly. So before we can say a molecule is optically active, that molecule must be chiral. The specific rotation of the enantiomer is equal in magnitude but opposite in sign. Now, when we say enantiomers, don't forget, enantiomers are non-superimposable mirror images of each other. We've said that before. So it means that both enantiomers, both molecules that are enantiomers of each other, they are actually identical, but their only difference is that they are mirror images, which means they cannot be superimposed. So we cannot say they are identical, but in all other things, they have the same molecules attached, the same atoms attached to the central atom, but they differ because they are mirror images of each other. And we've seen that before. Now, what you need to know is that the specific rotation of enantiomers are always equal in magnitude. That means if I tell you one enantiomer of tartaric acid is plus 45 degrees, automatically you should know the other enantiomer of tartaric acid will be minus 45 degrees. So they are always equal in magnitude, but they have opposite signs. So for instance, look at this specific rotation of some organic molecules. You don't need to memorize any of this. This is just here for example. We have penicillin. Penicillin is minus 233. So automatically, I know the other enantiomer of penicillin will be plus 233. Sucrose is minus 66.47. I know the other would be plus 66.47. In that, cholesterol is minus 331.5, which means that what? The other one would be what? Will be plus 33 and 31.5. But look at acetic acid and benzene. You can see their rotation is 0. It means both acetic acid and benzene are not chiral compounds. They are not optically active. If you see the structure of benzene, you see that all the carbons in benzene has double bond. So there's no way they can form a chiral compound. There's no way they can have a chiral molecule in benzene, a chiral center in benzene. So it is not chiral and it will not rotate a plane polarized light. That's why we have 0. Same thing with acetic acid. Now let's look at the Pasteur discovery of enantiomer. Enantiomers were first discovered by Pasteur in 1849. Pasteur discovered enantiomers in 1849. And according to Louis Pasteur, he discovered that sodium ammonium salt of tartaric acid crystallized into right-handed and left-handed forms. So when he carried out his experiment, he saw that the same molecule had the right-handed and the left-handed form, the same molecule of sodium ammonium salt of tartaric acid, and the optical rotations of equal concentration of these forms have opposite optical rotation. So he tried a racemic mixture of them, put the same quantity, equal concentration of both of them, and he saw they had exactly the same opposite rotation to each other. The solution contained mirror image isomer called enantiomers, and they crystallize in distinctly different shapes. So, and this is the shape that I brought up. They are both the same. The only difference is that they are mirror images of each other. So this is the sodium ammonium titrate. So this was the first compound that was used to discover what we call the enantiomers today, and it was discovered by Louis Pasteur. So, and of course, we have the positive and the negative form. They are equal in magnitude, but they have different signs. A relative 3D dimension structure. The original method was a correlation system classifying related molecules into family focused on carbohydrates. So correlates to D and L glyceraldehyde. D erythros is the mirror image of L erythros. So initially, when enantiomers, the concept of enantiomer was discovered, they were used mostly for carbohydrates. So we had what we call D erythros, L erythros, which you can see from here. This does not apply in general. Look at it here. We have your D glyceraldehyde, we have your L glyceraldehyde, we have your D erythros, we have your L erythros. Now you can see the way it is being named. When you have your OH on the right side, we call it D erythros. When you have both of them on the left side, we call it L erythros. But this method was used for carbohydrates. It is not the best way to tell whether it is a dextro or a level rotatory. But we shall see how, as time went on, we had more advancement, and then we had a better way to describe whether it is dextro rotatory or level rotatory. But this was how it was initially done. Once you see it on the right, once you see the OH on the right, for carbohydrates, it is a D glyceraldehyde, but for when the OH is on the left, we call it a L glyceraldehyde. So that was how it was named initially for the carbohydrate family. So sequence rule for specification of configuration. But now, since we are using this concept for even more than carbohydrates and virtually every compound in chemistry, we now have what we call a sequence rule. Now, a general method applies to the configuration at each chiral center instead of to the whole molecule. You can see in the previous one, I called D glyceraldehyde, D erythros, L erythros based on the whole molecule. But now we can name the sequence rule, help us to name it. Each chiral center will have its own rotation, that is its own name. Each chiral center will have its own naming. So the configuration is specified by the relative positions of all the groups with respect to each other at the chirality center. The groups are ranked in an established priority sequence and compared. They are ranked in priority sequence and compared. The relationship of the group in priority order in space determines the label applied to the configuration according to a rule called Kahn-Ingold-Prelog rule. Kahn-Ingold-Prelog rule is a rule that helps us to actually explain the sequencing and then prioritize each of the group to name the molecule. So we shall end the class here today, and next class we shall begin to look at the Kahn-Ingold-Prelog rules. We shall look at how to specify rotation to each of the chiral centers, how to specify priority to the constituent, and to determine whether it is going to be to the right, rotating to the right or to the left. So thank you very much for listening.